Thank you, Emily, for the introductions. Hello, everyone. So first of all, I want to thank the organizer for giving me the opportunity to share my work. Probably my last presentation with the Nanomedicines and Nanosounds or Nanoprobes teams. So my work will be on exploring reconstructed human skin and synthetic membranes as alternative to IVPT or in vitro permeation testing. Do you see my second slide? Okay.
Yes.
Okay, good, thank you. So, well, evaluating topical product involves conducting in vitro permeation test, IVPT, on skin, and of course, according to regulatory guidelines, European, but also international, like FDA guidelines. So this experiment aims to assess the permeation to quantify the amount of active ingredient that pass through the skin, and also to determine the penetrations profile of these active ingredients within the skin using some reference techniques like tape stripping method, but also some novel techniques like not really novel, but like Raman spectroscopy or confocal Raman spectroscopy. So these experiments are performed using bioanalytical methods to demonstrate the efficacy of topical products. So typically, IVPT tests are conducted using human skin or excised human skin, which is regarded as the gold standard for evaluating trans-drug delivery system. This skin is usually obtained from plastic surgery procedures. However, due to ethical concerns, limited availability, cost, and storage condition, the use of this excised human skin is becoming increasingly challenging. So to overcome the difficulties, several types of non-animal models are commercially available, like reconstructed human skin. Here we will take the example of EpiSkin at the day 13 days of maturation. I will explain more about this maturation days. This marketed model is one of the most widely used in pharmaceutical or cosmetic research and development. And despite their attractiveness, its relatively high cost may limit their use in pilot studies and or screening of active formulation. In third position, we have a synthetic membrane. It is used by researchers to eliminate the need of biological models. The Strat-M here, as example, is a synthetic polymeric membranes, offers some advantage such as no batch-to-batch variability and no safety or storage limitation. So therefore, the main objective of this work is to reposition the use of the different skin models for the in vitro permeation test using a multimodal analytical approach, which is one of our skills in NMNS teams. So for this purpose, a methodology was developed, including first IVPT permeation test using Francel. These skin models were exposed to 5% weight of resorcinol formulated in aqueous solution, hydrogel, and oil in water emulsions. The permitted amount was quantified by HPLC in order to compare the permeability and the formulation effect on the skin models. Second, the extracted lipid from the skin models was analyzed qualitatively and quantitatively using HPLC coupled with mass spectrometry in collaboration with Lipsisky from Paris-Saclay University. And the second step aims to the comparison of the lipid composition in the three skin model used in this work. So the IVPT test from the human skin, averaged here on 3 donors indicated that the permeability of the emulsion, represented in red circle here, was higher than than solution and hydrogel. This is likely due to the composition of the emulsion, particularly the surfactant. So regarding the EP skin, the permeability ranking remained consistent with emulsion greater than solution and hydrogel. This demonstrates that the aerosol replicate or EP skin replicate the formulation effect. However, if we take the example at 12 hours mark, the cumulative amount was about, in true EP skin, was about 1.6 milligram per squared centimeter compared to 0.15 for human skin, indicating that the permeability through the EP skin is about 10 times higher than human skin. So for the Strat-M, the permeability was similar across formulation. However, the formulation differed. This suggests that Strat-M does not replicate the formulation effect, likely due to its polymeric composition. However, it was amazing to plot the permeability of the emulsion as example here across the 3 skin models, and as shown, the permeability of the Strat-M, represented in blue square here, was closer to the human skin compared to EP skin, which is, as mentioned, 10 times higher than human skin, indicating that Strat-M could be a viable alternative for screening chemical compound with permeability values closer to human skin values. So to better understand the difference in permeability, lipids were extracted from the skin models and analyzing using HPLC-MS. The results revealed that, contrary to some literature report, the Strat-M membrane does not contain any lipids or any synthetic lipids. However, the EP skin and human skin have comparable qualitative lipid profiles, including triglycerides and cholesterol. However, difference remains in ceramide. So focusing on the ceramide region between 19 and 32 minutes, we observe 4 peaks, each peaks representing a class of ceramides, and a quantitative analysis was therefore performed on these peaks. So the results show quantitative differences, notably in peak 2, represented in orange here, which was 7 times greater in human skin compared to EP skin. So these differences impact directly lipid arrangement, resulting in a less dense hexagonal state on EP skin compared to orthorhombic and more ordered state in human skin. So this improves, this difference on the state improves directly the intercellular pathways and consequently the permeability, especially for a hydrophilic compound like a resorcin. So based on these results, we can redefine the application of different skin models. So the Strat-M models are suitable for screening molecules as their permeability values closely resemble to those of human skin, making them a cost-effective options. EP skin, however, could be an effective model for screening both molecules and formulation, offering higher permeability comparing to skin. So you have to take account these differences in permeability values. However, the questions remain about the storage condition of these models, particularly when multiple in vitro permeation tests needed to be performed with different molecules, concentration, and formulation. So in the literature, freezing human skin is a well-established method allowing storage for up to 1 year with a compromised barrier function, even with the use of cryo preservatives. So for the Strat-M, room temperature storage is sufficient for this polymeric membrane. However, the storage condition of EpiSkin still unknown, especially since the supplier recommended a shelf life of 72 hours after delivery. So what are the best storage practice for the the EpiSkin? So to address this, we developed a new method for storing EpiSkin involving a neutral buffer formalin fixation protocol. So initially, EpiSkin sample were fully immersed in 10% volume per volume neutral buffer formalin for fixation at room temperature for 24 hours. Subsequently, these fixed EpiSkin samples were stored in a dark room, in dark cold room, 4 degrees, until the day of the permeation experiment, using here a caffeine as a model compound. Then the permeation experiment were conducted in triplicate at T0, so T0 corresponding to the time immediately after the 24 hours fixation protocols, T0 plus 7 days, and T0 plus 21 days. And of course, fresh sample are used here as control. Secondly, to evaluate the impact of this process, we used Raman spectroscopy on the fresh and fixed tissues. And here the methodology was that additional EpiSkin samples not exposed to caffeine were prepared under the same condition at T0 up to T0 plus 21 days with a control. And these samples were removed from the cold room and stored at the -20 before being slicing using cryomicrotomy. And then spectra were recorded on both fresh and fixed samples. So the caffeine permeation results demonstrate that the permeability through the fixed EpiSkin at T0, T0 plus 7, and T0 plus 21 days was comparable of that to fresh samples represented in the red circle here. And the observed differences were minimal, ranging from 10 to 15%, with a maximum of 0.85 decrease fold. So the accumulated data here indicated that the barrier function in the fixed samples remained intact, albeit with slightly reduced permeability. And it preserved the limiting diffusion rate even after 21 days of storage. While there is less research on EpiSkin, our previous study performed by Danzig by Yuri have reported the impairment of the skin barrier function due to freezing, particularly in the case of resorcinol, which is a small hydrophilic compound, demonstrating that the storage of EpiSkin at -150, -18, and -20 degrees for 1 and 10 weeks resulted in increased permeability ranging from 3 to 6-fold compound of fresh sample represented in here, indicating that the freezing protocol compromises the barrier of EpiSkin. So while direct comparison between caffeine and resorcinol may present some challenges, it is evident that consistently storing sample below freezing significantly increase skin permeability. And in contrast, our finding demonstrate that chemical fixation with formalin leads to a minimal alteration of the barrier function. So the confocal Raman spectroscopy analysis combined with statistical techniques, including here principal component analysis, identified biomolecular differences between, as we can see at the scatter plot here, obvious difference between fresh represented in red and fixed samples. And this difference are attributed to biomolecular differences between fresh and fixed samples. These differences are associated with conformational change in lipid and proteins, especially affecting the amide-1, 3-phenylalanine, tryptophan, and tyrosine. And importantly, this change does not affect the barrier function of episkin when compared to freezing process. So, in summary, or to sum up our work, this study has demonstrated that the formalin fixation protocol offers a stable method for storing reconstructed human skin models without significantly compromising their barrier function, while molecular changes in various skin layers were observed by confocal Raman spectroscopy following the 24 hours fixation protocol. It is noteworthy that the permeation of caffeine remained consistent over a 3-week storage period. So, in comparison to documented effect of freezing in existing literature, formalin fixation results in only minor variation, approximately 10 to 15% in the cumulative amount when compared to fresh sample. So this work suggests that formalin fixation could effectively address one of the primary limitations associated with the use of reconstructed human epidermis models in permeation studies, their limited shelf life. So, although further investigation is needed to explore the specific biochemical changes in the episkin or reconstructed human epidermis model, this work highlights that chemical fixation may be less detrimental than freezing. This makes it a promising alternative for storing skin sample that closely resemble native skin in terms of structure and morphology. So that is the big question. And to finish, I want to thank everyone who contributed to this work, as well as my team represented in this lovely image. And thank you all for your attention.